So we continue then with the morning session with Arslan and Mazitov. He's a future student with the EPFL in Switzerland, and he's the main developer of MLIP. And he will today talk about universality in machine learning interatomic potentials. So, congratulations.
Thank you a lot. And yeah, I'd like to thank organizers first for inviting me and to giving me this opportunity to talk to you guys and then discuss and tell you what we do in EPFL and in this branch of, maybe not well adopted, but still very rapidly developing direction in machine learning potentials, which is the unconstrained models and unconstrained architectures based MLIPs. So the plan for today is to kind of make first a certain historical review of how we ended up developing the PETMAD potential, which is basically the core model that we now develop in EPFL in the group of Michele Ceriotti, and then to kind of express what directions we are exploring right now and where do we want to ideally come in the future. So let's first. Okay, doesn't work. Let me just maybe. Okay, no, everything's good.
Okay, yeah, I'm just gonna turn on the camera as well. So that people can see.
Okay.
Yeah. Okay.
Okay. Cool. Yeah. So, so the idea. Okay. So I think I'll probably skip this, first generic introduction of what MLIPs are. I suppose all of you knows what they are and why do we need them. The only very crucial point that I kind of wanted to bring up first is to notice that during the transition from this previous generation of MLIPs, which were basically very sparse in the chemical space, the models like GAP, MTP, or ACE, in their first generic formulations, were treating the chemical elements as basically separate pairs, triplets, quadruplets, and other combinations of elements depending on the body order of the potential. And basically, for every single combination of these elements, we were had to build a completely disconnected manifold of the features, and that basically gave us abnormal scaling of the model with respect to the size of this chemical space. So the sparsity is something that we don't like in the models, but in the same time, the universal models that like M3GNet first, and then MACE, and then all the other models that we know up to this point use a slightly different approach. They kind of try to learn this chemical space from the data by saying that all the elements, they in principle should live in the same exact high dimensional chemical space, and then the sort of the way to organize this space is what we tell the model to do, and we don't kind of tell the model how to do this. It decides itself, right? And it actually works quite nice, and it allows us to learn much more efficient representations of the chemical elements and cross-learn between different chemical elements as well. So another cornerstone of the modern MLIPs, especially the universal models, the foundation models as we call them, is what is called equivariance. And this is basically a fancy way of saying that when we have a structure or a molecule, spoiler alert, I will be mostly talking about materials here, and I will be sometimes switching into molecules, but this is mostly about materials. So if we take a look about on the crystal, right, we can rotate it, and then the equivariance means that the rotation, the prediction of the model on the rotated version of the configuration we put into, in this particular case, it doesn't mean, in this particular case, it doesn't really matter whether it's crystal or a molecule. The target that we predict should be rotated correspondingly. And of course, when we try to build in this concept into the architecture, what happens in the underlying naive implementation is that we actually start respecting different objects and classifying them in by the way they can be transformed under rotations and also inversions And this separation by the L channels and P channels inside the model actually creates also a lot of sparsity, because we basically need to transform every single object, like the feature vector of the corresponding L or P channel, with its own set of Clebsch-Gordon coefficients and Wigner matrices. And then, of course, it creates a lot of sparsity in the data as well. You know, all these complex maths and all these complex objects that we need to operate with to actually, you know, respect the equivariance gave birth to this meme. Then maybe we can just, you know, have this example as our own domain-specific version of Richard Sutton's bitter lesson, which basically tells us that sometimes we don't really need to reinvent the bicycles, and we just can let the model learn the relevant physics from the data itself. And this is what kind of made this foundation for the idea of learning equivariance, which is basically the idea that tells us, let's just get rid of all this sparsity in the model, which we use just one single set of features for whatever amount of, let's say, objects that we try to learn, whatever targets we try to learn, not really taking care of any kind of complexity inside these objects. We only need to do two things. We need to rotate our crystals or molecules during the training, and then we also need to make predictions on rotated versions of the targets. So that's how the model could learn how to associate these input and output features with respect to each other. And yeah, so this is kind of, you know, a foundation for what ideas we had when we started developing PetPlan, because of course, in the historical perspective, it's important to know what kind of issues existed there. And you know, in most of the cases, I'll be taking here a snapshot of a data which was rather like around a year ago, but I think it's still important to see how this evolution happened in this historical dynamics. And around a year ago, it was basically like this. So if we take a look about on the snapshot of the models that were available back then in the material discovery benchmark, we basically see that all the state-of-the-art models like ESEN or MatrixSim or ORB or even Genome were trained on the very large data sets, and they were basically very large models. And well, the question is that we kind of didn't know whether it's necessary to have this large amount of data and parameters inside the architectures to actually achieve good performance. So at the second time, I think now this question is way more, let's say, well treated and processed. But 1 year ago, it wasn't like this, and we already have seen that kind of, you know, we have inconsistencies in the training data. Maybe this is not what typically you guys will see in the chemically and biochemical molecules and structures and configurations, but in the highly correlated oxide systems, for example, we can clearly see that, you know, some of the parts of the training data that were used to train the universal models were actually computed with two absolutely inconsistent settings, which are +U and no +U correction. And when we combine these kinds of data inside a single data set, it creates us a huge problem, because the inconsistencies just limit the amount, limit the accuracy of the model that we can have. And finally, most of the data sets back then, again, were kind of designed for materials discovery purposes, and they mostly consisted of stable materials. They didn't have kind of, you know, cross data, let's say, there were basically no data sets that consisted of both materials and molecular data computed at the same level of theory, a consistent level of theory, and also we didn't have much low-dimensional structures as well. So we kind of, if we want to say that our model is universal, we in principle need to treat all these structures in a rather similar way and train on all of them, right? And well, this was the foundation of the PetMat model, which we designed following two different directions. The first one was the data design direction, and the second one was architectural decisions. Data-wise, we developed this massive atomic diversity, which is the MAD part of the PET-MAD dataset, and it consisted of 8 classes of structures, while being also very restricted in the overall number of configurations itself. We kind of decided to try to be as data efficient as possible by introducing the ideal crystals. Also, their rattled counterparts like this. Okay, it works. Cool. So the random structures, which consist basically of the randomly associated set of elements that is just placed onto lattice sites, the isolated clusters, and also a bunch of other low-dimensional structures like surfaces and two-dimensional materials. And finally, we had this subset, which was consisted of molecular crystals and neutral molecular fragments. And overall, we had covered about 85 elements and computed all of these structures within the single consistent DFT protocol to avoid all possible, data inconsistencies in the targets. And we try to learn this with the point edge transformer model, or PET in short, which is the transformer plus GNN unconstrained architecture. And by design, I don't know why it doesn't work, but anyway, which is by design, follows the same principles as all the other models in the field. It basically tries to build the feature representation of the atomic environment by associating the feature vectors with all the particles in the cutoff radius, and then by encoding basically the distance and the chemical identity of these neighbors by applying these feature vectors, and then forcing these feature vectors to talk to each other by repeatedly calling these update and aggregation protocols based on the combination of the graph neural network and transformer architectures. And finally, we have this multi-layer perceptron head, which gives us the energies and forces of the model. So let's take a look a bit closer to the architecture itself. So the basic idea, and I try to probably use this one. Yeah, so the basic idea here is that we always start with the set of indices that are associated with the atoms in the local atomic environment, and then also the chemical species, and also the Cartesian coordinates of the bond vectors. And the overall architecture works like a large block, which is repeated like n times, which is called the GNN layer. And then by calling this block many times, we kind of try to learn the feature representation of our structure, right? And then finally, when we have the feature representation, a certain mathematical construction that tells us how to transport from the raw Cartesian coordinates and chemical species to the feature space that kind of learnable feature space of the model, we can apply finally something called the head, which is basically the way to make a last step from the feature space to the target model, to the target prediction that we are interested in. And then inside each of these blocks, we have these basically 2 data streams that are encoding the node features and also the edge features associated with the atoms and the bonds between them. Both carries feature vectors that are flowing through the transformer block, which basically applies this multi-head attention mechanism, and then just basically forces the feature vectors to talk to each other. And then by doing the message passing, in the end, we kind of aggregate all the messages inside from the nodes to the edges. Sorry, from the edges to the nodes, and then repeat the process once again. And finally, once we have the final representations of the nodes and of the edges, we sum up the representation of the edges to get the final representation of the nodes and make a prediction. Regarding the data set, we basically, as I said, have a rather restricted version, which doesn't exceed 100,000 atoms. And we have all these 8 subsets of the data set, which are, as I said earlier, the log structures, but then also their rattled counterparts, which have this, shifted, tilted positions of atoms. And we do this because we want to induce a certain amount of force that acts on atoms in the system, because we basically learn the potential energy surface in the end and also its gradients, right? And then we also have these randomized configurations, which are built by basically setting the, taking the large, taking the unit cell and then associating the random elements with this unit cell. And this is basically our way to add a certain level of stability to the model, because in many cases, when the model starts seeing the unreasonable configurations without training on them, it just panics and can blow up and do some other random stuff which we don't like. And then having such structures inside the data set can help to stabilize it. Even though these structures can never be seen in the real simulations, it can actually be helpful for the model to stabilize its dynamics behavior. And of course, having the low-dimensional structures helps either, because we basically sometimes want to simulate the nanoclusters or the molecules or the surfaces, and this is what makes the model universal. You put inside anything and it just works, right? At least ideally. So if we take a look at the visualization of this data set, the MAT dataset, we can see rather following picture. So as I said, again, we have this 8 subsets, and the nice thing about this visualization is that it actually allows to separate some of the classes of the systems. For example, the clusters on this large plot, they are associated with a single blob that is kind of separated from other ideal crystals and also the rattled crystals. While the randomized crystals, even though they are rather sparse because we have relatively low amount of these structures, actually covers a really large amount of space in this feature representation, low dimensional feature representation. And the nice thing about, for example, of this visualization is, for example, the chemically restricted biofragments and molecular fragments, they actually are represented as these relatively narrow lines, which means that we can even like induce a certain chemical interpretation of these components, where we kind of have something associated with the chemical diversity along y-axis, which is relatively small in the case of biomolecules, but rather molecular structures. And then in that case, we have relatively large and diverse variance across the second line. The first line, of course, the first coordinate is a bit harder to interpret, but it can be somewhat associated probably with the amount of atoms in the system or the average density of the system. It's also interesting to see how these data sets are, these subsets are, how the subsets are distributed in the target space, and we actually can see that how large can be a difference from the idealized structures, which kind of contribute to the most of the old EVA training data sets, and having a relatively small force modulus and relatively narrow range of energies. And of course, when we kind of extend this representation to other systems like randomized or rattled, we see very much larger forces and very much larger energies that also can help to kind of provide the boundary conditions for the potential energy surface. Thing that is also rather interesting to see is the relation to other data sets, because we kind of claim the larger diversity, but whether it's large indeed. And what we did here is basically sampled a few subsets from popular machine learning training data sets from the times around 1 year ago. We took the Alexandria MP trajectories data set, also the catalytic OC 2020, also the molecular spice and the MD22 data set. And we basically tried to plot this subsets of these large data sets, also the subset of MAD, and basically to analyze how the pairwise distances between the structures are represented. And this is kind of the histogram of these pairwise distances, which you can see in the insets. And the nice thing about this visualization, it actually allows to see that in most of the cases, even though the short pairwise distances have large density in almost all the cases, because the structures apparently are more densely packed in the feature space. In most of the cases, we have this tail that kind of exceeds the tails of all other datasets, which means that in MAD, we have very much larger coverage and more structures with distance features that in the feature space, which kind of, even though they are relatively sparsely located, but still for the sake of coverage and universality, it's a good exercise to have. Let's talk a bit about the figure that we have seen before once again, right? So it's really interesting to see how PetMat performs, basically being trained on this data set. How does it perform on the same exact task? So the interesting thing that we kind of land at this particular place in the plot, and the idea would be that if we just train on the data, train on the MAD data, and then we evaluate against the materials discovery benchmark, that we land somewhere here. So we push down this frontier of the data efficiency and reaching the accuracy of other models like Mattersim or GNOME by using 10 to 1,000 times less data, which is really cool. But there is a problem with this plot, which is if we naively evaluate the model against the materials discovery targets in the MAD-based discovery benchmark, we get a very much larger error. And the reason for that is the inconsistency in the DFT itself. Because if we just compare the targets themselves, which are located on the plot and depicted with this red blob, we actually see that the difference in DFT can reach 120 MeV per atom. And I'm not sure how to, probably like 3 kilocalories per mole, if I'm not mistaken, but please correct me if I'm wrong. So it's a large error, and it's only associated with the inconsistencies in the targets themselves, which of course limits the accuracy of the model, which is trained on this data, right? And then if we recompute the data with using the same exact consistent protocol that we had in the PetMAD, of course we can get way more accurate model in the end. So it's interesting to see also how PetMAD behaves in the benchmarks, and to do so, we basically evaluated it against a few different benchmarks like inorganic crystals benchmarks, the catalysis, and also the molecular systems, which I have mentioned earlier. And we referenced against a different available model which were available again around 1 year ago within this study, and we evaluated against all consistent DFT targets by basically recomputing the subsets, the benchmark subsets with the PetMAD settings for consistency with PetMAD, and also for models like for datasets like SPICE or MD22, we were recomputing the same exact structures but using the settings used to train the MACE or ORB models, even though the original DFT data was computed with another methods. And of course, this is for the sake of consistency. And this is the result we get. So basically, in most of the cases, we see that in these energy error and force error plots, we have the circular diagrams, and basically the closer we are to the center, the better, because the smaller the error is in that case. And in most of the cases, we see that the black line, which is the PetMAD, kind of is closer to the center in both energies and forces, except for probably the MP trajectories and Alexandria datasets, right? Because it actually turns out that these two datasets were the training sets of these orb and Mattersim models, and in that case, of course, the data leakage can be the reason why we get this problem for these two models. And of course, the same states for MAD, because MAD is trained on the PetMAD is trained on MAD dataset. This is no surprise that it gets good accuracy on its own training data. But still, it gets the good accuracy on these new benchmarks, that on these different benchmarks, even though it is actually trained on a different kind of data. So it's purely extrapolative exercise for the model itself. Okay, so benchmarks Of course, they are great, but they don't tell us the full story about the model, right? We need to see how the model performs in realistic applications, and this is what we did inside the lab, and with the help of Davide, with the help of Paolo and Matthias. But this is what basically happens in this slice, is that we compute different properties of materials like ionic conductivity in the lithium thiophosphate, the dielectric effects and dielectric constant in the barium titanate, and then also the melting point of the gallium arsenide. And in all these cases, we can see that PETMAD doesn't fail. It predicts something. The question is how accurate this prediction is, right? So luckily, for each of those three systems, we already had the system-specific data sets that we can use to train system-specific models and then compare PETMAD against these models. And this is what we did. But we also did one more thing. On top of that, we trained the LoRa version of the fine-tuned model by basically training the PETMAD and fine-tuning it on this system-specific datasets. And the results that we get are basically on this plot. So in the case of lithium thiophosphate, we actually get almost identical predictions, which is basically telling that the PETMAD can be used from scratch out of the box without even requiring too much fine-tuning. In other cases, a little bit fine-tuning would help to improve the accuracy, but even like the original predictions are relatively close in both these cases, in both the barium titanate and gallium arsenide systems. But still, of course, these examples show that even out of the box, the model can be reliably used for computing different properties which are rather distinct, and this is great. Of course, not only these, but also some other applications can be done. For example, the prediction of the surface segregation in high entropy alloys. Another very interesting example when we see basically the soup of 5 elements, and when we try to predict in the relaxed state and in the long run what elements will be at the surface and what will be at in the middle of the sample, and then again we have relatively close agreement between the results. And also for example, other completely disentangled domain is the NMR crystallography, where we can see that PETMAD also achieves very nice interpretation of the chemical shieldings that are relevant for the NMR crystallography, and also the nuclear quantum effects in water that allows us to get a relatively good description of the heat capacity. And in all these three cases, PETMAD, the raw PETMAD predictions are actually quite nicely agreed with the bespoke and the fine-tuned versions of the models. But the main problem in MLIPs is, okay, maybe not one of them, but one of the most important issues that can arise is the model failing silently. Basically, the main issue is like you run the simulation, you don't sure exactly when it will fail, especially if you're kind of working in a domain which is known to have relatively little interaction and cross-section with the training set of the model itself. And of course, the certain uncertainty quantification is a tool that would allow you to kind of know in advance whether the model is doing something wrong and is prone to blowing up and to corrupting your simulation. This is what we do in PETMAD by employing this shallow ensemble UQ that is basically the ensemble of last layer features, the last layers of the model. So instead of just predicting the 10 different copies of the model and averaging the result, we're predicting 10 different last layers representations, and then we predict the result and the uncertainty based on these predictions, and the average the result over this prediction. And basically the idea is that once we have this kind of uncertainty, we can actually propagate it back to the data. So back to the target that we try to predict from the simulation itself. In that case, if we take a look on this example of the melting point, we actually can see that in that case we had these original prediction, but then when we applied the UQ we get the picture that looks like this. We basically can see that the original prediction of the model can be a range from 1,000 to 1200 kelvins, and then we can actually see this kind of large error, or whether it's large or not large in the first place. It's the question that we need to answer ourselves, right? But then if we see that this uncertainty is not satisfactory, we can actually fine tune or decide to I don't know, use a bespoke model, whatever. And of course, when we do so, the uncertainty actually shrinks down quite massively. So if you take a look at this picture, for example, we actually have, all the predictions like condensed into the same exact region around the line. So that's how accurate it becomes after the fine tuning. So yeah, of course, everything is good until we start doing the simulations themselves, right? And in many cases, we can see the models just being a bit slow and not satisfactory fast for us. Hopefully with PetMat is not the case, because we have a full GPU support in LAMPS with the Cocos implementation of the code. And in that plot, we can basically see that in almost all the cases, PetMat is faster than other models that we benchmark against. The main problem is that we have one competitor, so to say, the ORB model, but the key difference of ORB is that it's a non-conservative model, which actually doesn't compute the forces using the automatic differentiation tools from the predicted energy. So we kind of comparing apples to oranges, and to compare oranges to oranges or apples to apples, we actually trained the similar version of the PetMat model, which actually has the non-conservative forces as well. So we basically just predict forces as separate targets, independent of the energy, and in that case we can get a factor of 2 to 3 speed up in the model speed. I think at this point the main question that kind of flows in the air is, we were talking about the model which is non-equivariant in the first place. So should it be important for the simulations? How we can mitigate the problems and issues and inaccuracies that can be induced by the broken symmetries in the model? And this is actually what Marcel and Sergey have studied in our lab. The interesting effect is that first, it's important to just evaluate how large the error which is associated with the broken symmetries, with the lack of equivariance. And the way to do so is to take the same exact structure, rotate it randomly, or actually in a very good distinctive way using the Lebedev quadrature over the unit sphere to see how large would be the standard deviation of the predictions. And this is what we did. And we also compared against ORB v2 model. And in most of the cases, we see that the prediction error is quite small. It actually goes below 1 MeV per atom. And in that case, we can see that it's way smaller than the error of the ORB v2 models, especially on the molecular fragments, the small molecular structures. So it's already good, but 1 MeV, it doesn't mean that it's a zero, right? And the main problem with this approach is that this error can start accumulating at some point. And this is what we see, for example, in this simulation of a single water molecule. Because if we take a look at the projection of the angular angular momentum of the molecule, we can see that it starts oscillating in time, and of course this is associated with the lack of equivariance in the model. So the way to deal with this problem is to actually average over different rotations. So we basically spawn different rotations of the same exact structure. We make the prediction, we rotate back the predicted forces and energies. In that case, energies are not changed, but forces are changed, right? And then we kind of provide the averaged example. And that cures everything. We see that the property becomes conserved and it doesn't change in time. But the main problem is that it's not really satisfactory, right? Because it basically increases the cost of evaluation by so many factors that we basically lose all the power that we kind of tried to acquire first by getting rid of the getting rid of the sparsity associated with the equivariance in the models, right? So it doesn't make any sense. Well, the nice thing about this rotational averaging is that it can actually be, at least inside simulations, inside MD simulations, it can be fixed by a different approach, which is called random rotational augmentations. And the idea is that on every single time step during the simulation, we can actually rotate the structure somehow randomly, make the prediction, and rotate the predicted forces and stresses perhaps back to the original frame. And that gives us the same exact effect as the averaging over the grid, but just doesn't cost the 10 times or 30 times more as the averaged rotation, averaged prediction. And you can see this on the example of the liquid water at 300 kelvins. We see that the G of R is exactly the same. The dipole autocorrelation function is exactly the same. The diffusivity is exactly the same. So we can get between these two curves, we get exactly the same behavior in both cases. And it basically allows us to save a lot of compute. And the final idea is that, as I mentioned, we can also use the direct forced MD. And that's a way to get another 2 to 3 speed up. But the main problem with the conservative, non-conservative forces is that we lose conservation of energy, and that's not good. Of course, but we can actually deal with this problem using something called multiple time stepping integration paradigm, which is basically the way to, once per 10 or 15 time steps, for example, or 8 time steps, we call the conservative model, and then all the intermediate time steps we do with non-conservative prediction, which is fast, and then we kind of correct the error which can be accumulating through these steps by the conservative model once per n time steps, and then we choose the n to balance the accuracy and speed, basically. So this is also the way to see how this basically helps conserving the energy in the NV ensemble, and the NVT ensemble, it actually allows to basically balance the thermostat as well. So again, even though we have unconstrained behavior, we can actually correct it and mitigate the issues related to the lack of accuracy. Okay, so before going to the scaled versions of the models, because at some point we actually decided that probably we can try to scale up the calculations as well, even though it can be very expensive, but whatever, like why not to try, right? The main problem with the large data sets, with the large structure systems, very diverse structures, is that we basically can have in the same exact data set structures that we that are kind of that have different densities, right? And when the structures have different densities, in the same exact cutoff value, we can have different number of atoms in the system, and that number can differ a lot. So the solution to that issue is to use the to transfer from the fixed cutoff radius to the fixed number of neighbors. And this is what the adaptive cutoff idea was implemented for. So it works something like this. We define basically the grid of different cutoff values around the central atom. And then we kind of make this indicator function that basically is the cutoff function of the model. And it basically tells us how many neighbors are located in the cutoff sphere of a radius r. And then we can change r and then sample this a function that looks something like this. So first we have no neighbors, then we have like, starting, this number starts growing, we have 1, we have 2 neighbors, and so on. And the idea is to solve this equation, solve this curve with respect to the number of target number of neighbors, and also get what kind of cutoff value we will get in the end. So this is what we do. Basically, we have the solution as a weighted sum of the spawned cutoff values, and then we apply this softmax-like function to get the weights, where we basically replace the exponents with the Gaussian functions, and in the end, we can also see that the final value of the calculated adaptive cutoff radii actually giving us the correct number of neighbors. So for 20 neighbors, we get on average 20 neighbors in the cutoff radius. For 30, we get roughly 30, and so on. And if we just have used the fixed cutoff radius of 6 angstroms, we sometimes get 100 neighbors in the cutoff. Sometimes we get like almost 0, which is, of course, not the good idea to have in the model where we train on the very sparse data set. So, and the nice thing about this approach is that it actually scales quite nicely, only linearly with the number of edges in the data set. So we entered with this large training scale training exercise, the MAT bench discovery, and this time this is the recent result that we get, and we kind of can see that now the PetMat OAM XL is taking the 6th place, while maybe like 5 months ago it was the #1. So the field is changing quite rapidly. And of course, a lot of efforts are done to finish this exercise as soon as possible. So, one thing that we can see is, of course, the actual differences are quite narrow and small, and we, rather need to think about more about the better data sets and the better training implementations, or model implementations, speed of simulations to get better future MLIPs. So I probably will be speeding up right now a little bit. I just wanted to say that, starting from the large pre-trained checkpoints actually helps to decrease the number of epochs that's required to train the model and to substantially decrease the error. And now we have like 5 different sizes of the models available, and they are rather fast, especially compared to the UMA model, for example. We from Meta, we can actually do a bit better than UMA. The next directions of the development are the MAD 1.5 direction, which is basically the extension of MAD dataset, which is computed by within the all-electron Archer-scan DFT, and covers all up to 102 elements, and includes a bunch of new structures to increase again the structural diversity. So the PetMat 1.5 is already available. It performs quite nicely. It has very low errors on the validation set, at least, and allows us to model very extreme systems like this Mendeleev clusters, for example, the combination of 102 atoms, and in almost all the cases, it really provides large, not so large errors, even in this completely out of sample example. And you can basically start using PetMat even right now. It's very simple, and I think by saying this, I will quickly skip to the last slide, where we can find all the people that helped me in this project, which I want to thank. And I invite you to try PetMat yourself and see if it works for your particular case. Please let me know, and you will find all the contacts in the GitHub, and also in the repository that we have with the code. We have the support of the new users, so please let us know if you see some problems with the simulations. And by saying so, I'd like to thank you a lot for your attention, and I'm happy to answer all the questions if you have any.
Thanks a lot. From the audience. Well, you have one question in the chat. In fact, 2. So they're asking, the first of all is, if we train the machine learning potential using configuration from room temperature to well above the melting point, including both solid and liquid phases, does the uncertainty during the phase transition become negligible, or is additional active learning around the transition still required?
So is it a question about what we did, or what?
I think it's in general, like, what do you think about the training machine learning potentials using like low temperature configurations and then try to extrapolate to phase transitions? Or
from my experience, that almost never works. So unless the low temperature configurations were somehow very aggressively rattled, I really doubt it's possible to reliably cover this phase transition, at least if no other phase transitions of other systems were presented in the training data. So maybe there is a certain cross-loading that can be happening, for example, between, I don't know, like covalently bound metals, I don't know, silicon to carbon, carbon to silicon, for example. Maybe in that case, it will work with a certain assumptions, but if it's just, the model which is trained only on lattice dynamics of a low temperature phase, and then we kind of try to extrapolate, probably it will not work. Yeah.
And then,
yeah, I have a question. So we have a slide, very nice talk, first of all.
Thank you.
Of like this slide of the third classification.
Yep.
It shows like the original model, the assumed, the stock model.
This one?
Yeah. So I have a question not about uncertainty, but about this blue and orange lines. So later you showed that fine tuning shows much better accuracy in test service, but it seems like the performance in dynamics is almost identical. Is this the case?
You mean the performance in the...
Just the values that we get to feel and stopping the channel, right?
Yes. That basically means that no matter what. So what are you asking about the costs of the or
I'm asking, but it makes sense. So here, for example, it looks like you can just train this stock model. There is as good as fine-tuned model.
Yes, but the main. Yeah, I got your question. So the main answer to this question, I'm not sure if I have this, but I think I do, is the speed with at which you kind of try to basically is how many configurations you need to put into the model to actually achieve that result. Basically, the idea is that in many cases, when we start training the bespoke model, it actually requires a lot of data to reach the good values. And in many cases, we can use something like, I don't know, 10% of the training data to actually get already good results with the fine-tuned version of the model. So that's the basic difference. You need less data than what you probably would have to use for the bespoke model. Yeah.
Okay. And then there are two kind of other related questions in the chat. Luis and Asif, they're asking first of all in slide 19. I highlight the difference on the number of parameters that PET uses versus other MLIPs.
That's a very good question. Yes, thank you for asking this. It's actually quite a lot, but these parameters are very nicely packed and very efficiently packed. In that case, you can see that even though it's like 10 times more parameters than typically we have in other models, the performance of PET-MAD is only, let's say, relatively, sorry. So it's basically comparable to other models. Like it's comparable to UMA. It's a bit slower than the NeQuip OAM-XL model. But if we talk about the XL version of the model, right? But it's faster than UMA, because in that case, the inference speed means how many seconds do we need to perform one single evaluation. And in that plot, we see that in almost all the cases, we are faster than UMA, even though we have like 10 times more parameters. So let's hope this will this will answer the question. Yeah.
Yeah. I'm also very interested in the quantitative modification. Because I wonder to what extent a linear relation between the algorithm and the trend to be able to do this kind of.
It's actually not. It's actually a bit more subtle. I'm not sure if I have this. Probably okay. Actually, I have this kind of plot. So basically, when we compare the predicted uncertainty against the actual error of the model, we are working with a certain probability distribution. So the number that we predict is a sample from a certain probability distribution. In the same way as you can sample a number from the Gaussian and say that, for example, 0.6 is a number from the Gaussian distribution with the standard normal distribution. In the same way, the uncertainty that you predict is a certain number that is basically centers the distribution of the uncertainty, the distribution of the final error that the model can have. So it only like centers you a certain value that you can expect, but the final error can be within this probability distribution, which can be shaped in different ways. Yeah.
In some cases, you mentioned that you can mix, you can use the direct model with the accurate model. You can run some direct calculation for, let's say, 8 steps, and then switch to the converting model. So I wonder if we can combine the uncertainty with this kind of
So you'd like to extend the time scale at which basically you apply the conservative prediction. I think that's a good idea, actually. I'm not sure we tested this, but that makes total sense. Yes, in principle, if you have a relatively low uncertainty in the direct prediction, why would you apply the increased time step? It's an interesting question. I think we need to take a minute to think about it. Thank you. Yeah.
Let's maybe continue the discussion in the coffee breaks.
Yeah, thank you.
So let's thank again the speaker.